Hi, today I'm going to talk about tuples in Python 3, specifically what is a tuple and why you'd use it instead of a different data type like a list. So in Python, a tuple is a built-in data type, meaning it comes with the language, or sequences, meaning collections of 0 or more elements of data. Right away, you might think of another built-in Python sequence, like a list, and ask, how is a tuple different from a list? Well, here are some key differences. You create a list by enclosing elements in square brackets and tuples with parentheses. Tuples are smaller than lists, meaning they take up less size in memory, approximately 80% of the size of a list. And tuples are immutable, meaning they can't change. And I'll go over each of these in more detail as we go on. Some similarities between tuples and lists. They're both Python sequences, meaning you can unpack them, access elements by index, iterate over them, slice them up, check membership in them, get a count of objects in them, and get locations of the elements that are members of the sequence. Tuples and lists are also similarly quick to use in terms of creation, unpacking, iterating, and accessing elements. I think it's a common myth that people repeat frequently that tuples are faster than lists. But as we'll see here, tuples and lists are actually about equivalently quick to use. So let's talk about creating tuples. There are 3 ways to do it: without parentheses, with parentheses, and using the constructor function. So here we have an example of creating a tuple with no parentheses. We've just declared the elements that we want to be in our tuple. Here a tuple named no parentheses. And we've just written the elements separated by a comma, 5, 6, 7. Another way to do it is enclosing these elements with a parentheses. And if we wanted to create a list, we'd wrap these elements with square brackets. But as we want to create a tuple, we wrap it with parentheses, and we create a tuple named parentheses. Or we could use the constructor function, tuple. And here we create a tuple from a given sequence. So here I've supplied the list 5, 6, 7 as a sequence, as an input to my tuple constructor function. And I'm going to get a tuple, which I'll call constructor function, which is equivalent to the tuples that I created with these other 2 methods. So that's 3 ways to create a tuple: no parentheses, wrapping it in parentheses, and using the tuple constructor function. And as you can see here, they're all equivalent to each other. Now here I've written a method, which we're going to use as we go on, which creates a random sequence. And this method takes 2 arguments. The first is a sequence constructor function, which I'm calling S here. And the second is in, meaning the size of the sequence. And what this function is going to do is create a random sequence for us. And that's something that we'll use for testing some claims later on. So what it does is it simply returns the result of invoking the sequence constructor function that we were given, called S. And what we have in here is a generator expression, or a generator function. Now, to just explain what this is doing, we're saying we're going to get a random number between 0 and 1000, a random integer, I should say, for every value in this range. So in Python, the etiquette, or the proper way to write something when you're not going to use a variable for your for loop is to just use an underscore. But I could easily call this A or B or I or whatever. But I'm just calling it an underscore to represent the fact that I'm not going to use it. So the generator function says for every element in this range, we want to do this. We want to produce or generate a random integer between 0 and 1000. And then we're going to pass all of those generated things to the invocation of the constructor of the sequence constructor function, S. So we can use this real quick just to get an example of what it looks like. We could say create random sequence, and if we wanted to create a random tuple, we would pass the tuple constructor function and the size, the number of elements we want in our random sequence. So this would create a list of 3 random elements. Pretty straightforward, and we'll use that for testing some claims later on. So I referred earlier that a tuple is typically smaller than a list. And here I'm talking about sequence size. So in memory, tuples are about 80% the size of lists. They're similar size on the disk, and so that may raise a question, why are lists bigger than tuples? We'll answer that. So here I'm going to kind of prove the claim that I told you, that tuples are about 80% the size of lists. So here what I'm doing is I'm creating a list called XS, or X's. And to create this list, I have a generator function again, a generator expression, wrapped in square brackets. And Python will understand this to mean that I want to create a list of the results of this generator. So the generator is in for in range 1 to 101 and increment by 10. So this will give me 1, 10, 11, 21, and so on. And that'll give it to me in a list called X's. Then I want tuple sizes. Again, I've got a generator function here. And what I'm going to do is use the sys get size of, and that'll tell me the size of an object in memory, in bytes. And what I'm going to pass to this get size of function is a random sequence. Using the create random sequence, I'm going to create a random tuple of size n. And I'm going to do this for each n in our XS list. So the XS list we can see here is just this 1, 11, 21, so on, all the way up until it would exceed or meet 101. So I'm going to create a random tuple of these different sizes, and that's going to be the size of those random tuples is going to be what's stored in tuple sizes. And then I'm going to do the same thing for list sizes. And here I'm just using matplotlib to plot the results that I calculated here, to plot those as a bar graph. So basically what we can see is what is the size in memory of a tuple when there's one element of a tuple in blue and a list in orange, when there's one element in the sequence. And basically we see a pretty similar pattern for all these different sizes as we go between 0 and 91, or sorry, between 1 and 91. And you can see that in pretty much every case, the list is just a bit bigger, well, maybe more than a bit, about 20% larger than the tuple. And in fact, we can be more exact. We can calculate the average tuple size of a list. So here, I guess I'll walk through this. We're just, I guess let's go through the inner part first. We're zipping the tuple sizes and the list sizes, meaning we're creating a list where the tuple size is paired to the list size. And then we're going to, I'm just realizing this is slightly awkward to explain, but we're going to reduce that zip using an accumulator and an update variable. And the accumulator will just get the ratio of the tuple size over the list size and add that all up into the accumulator. And then once we've done that, we essentially have the average ratio of the tuple size to the list size. And then we'll just convert it to an int after multiplying it by 100 so that it looks like an easy to read percentage value, meaning it's a 2-digit integer rather than 0.82. It'll be 82. And when we print that out, we see that the average, we see that on average, the tuple is 82% the size of a list. So I think that pretty well matches what you can see here on the graph. The list is consistently bigger, though sometimes it's closer in size depending on the number of elements you have. So you might ask, why is that the list is significantly bigger than the tuple? And the answer is because when you create a list in Python, Python expects that you might append elements to the end of that list. And so because Python thinks you might append elements to the end of the list, it allocates more memory than you strictly need when you create a list. So it'll allocate additional memory, more memory than you need, so that it is efficient to add elements to the end of your list or to append it. Because a tuple, you cannot add elements to the end of a tuple or at all to a tuple. Python doesn't allocate any more memory than you need. So that also explains why there is a difference depending on the number of elements you have. Depending on the number of elements you have, you are using more or less of the memory that's allocated for you, if that makes sense. So there's another kind of interesting property to this, which is that it's only true that a tuple uses less memory than a disk, or uses significantly less memory than a list when you're in memory. So here I've just created a big tuple. So this is a random sequence of, let's see, of a million integers, a big tuple, a million integers long, and our big list is just a list with the same members as the big tuple. And so then what we're doing is using pickle, which will let us save these Python objects to a file, to save these two Python objects to two different files. So we have the big tuple file and the big list file. And when we get the disk usage of these two files, we see that big tuple takes up 2,680 bytes compared to the big list's 2,684 bytes. In other words, kind of no matter what your list and tuple sizes are in memory, the list is just going to take up 4 additional bytes compared to the big tuple. So while lists are substantially bigger in memory, they aren't really that much bigger if you're saving them to disk, using pickle at least. So here's something I already mentioned. Lists allow you to append elements. That is, you can add them at the end. Because Python expects that you might append some elements to your list, when memory is allocated for a list, extra memory is allocated so that you can efficiently append values to your list. But the trade-off for this is that lists take up more memory than the more efficient sequences like tuples. So being able to append items to a list and not to a tuple is related to what's probably the most significant difference between lists and tuples, which is that tuples are immutable. Immutable means that something cannot change. In Python, lists are mutable. They can change. You can add elements to a list. You can assign new or different elements to the indices of your list. You can remove elements from your list. Tuples, on the other hand, are immutable. Once created, a tuple cannot be changed. One advantage of an immutable data structure, like a tuple, is that because the structure cannot change, you know it's not going to get into an unexpected state when you are using it. You know that no matter what usage pattern you're following, that an immutable data structure will retain the state it had when it was created. And so that can make immutable data structures easier to work with and to reason about, and to help you when you're debugging. You'll know what state it's in, and there will be whole classes of errors or bugs that simply won't be possible to get with an immutable data structure. Another advantage to using an immutable data structure is that it can be stored as the key of a dictionary. So suppose you have a sequence of data that you want to store as the key in your dictionary. If you tried to use a list to store the sequence of data as the key in a dictionary, what would happen? Well, here we have an example. Here's our dictionary, a dictionary. And we have this list, a list, 567. And here we're trying to store in the dictionary, using the key, a list, this string. My key is the list 567. And you see that we get an error when we try to do that, a type error. You get a type error on hashable type list. Break that down. The type error is because the type, i.e. a list, of your key is incorrect. It's not supported. And it's incorrect because a list is mutable, and therefore it cannot be consistently hashed. Or maybe it's more accurate to say the list is not hashable, so therefore it can't be used as the key of a dictionary. A hash function is something that converts some object into a number. Importantly, the same object always gets the same result from the hash function. So if an object is mutable and the object changes, then its hash may change. A dictionary uses the hash function to store and retrieve keys and elements. If the hash of a key changed, then the storage and access of a key element pair would be unreliable in a dictionary. Let's see a simplified example of this with our own dictionary. Here I've just declared my own class. I'm calling it my dictionary. In the init method of the class, which will be invoked when a my dictionary object is created, what I'm going to do is I'm going to set the data property of self to be this list. So it's none for everything in range between 0 and 100. In other words, we're getting a list of 100 nones. And then when I put something in my dictionary, I'm giving it a key and a value. And what the put function is going to do is it's going to calculate an index. And the index is going to be a hash of our key, meaning we're going to take some object and get an integer from it. And then we're just going to take the modulo of the length of our data. So we'll pick some number between 0 and the length of our data list. And then we're just going to say self.data subindex, the index that we calculated with this expression is just going to get our value that we're trying to store. And so the simple reverse of that is the get function, which again calculates the same index and returns whatever is at that index in our data list. So this is just a very simple way of thinking about how a dictionary might work. This would let us insert and retrieve elements at constant time using the hash function. So here's an example of this. I'm creating my dictionary. I'm putting in, using the key 1, the string hello, using the key 2, the string goodbye, and then I'm getting the value at the key 2, which is goodbye, correctly stored it. So hashing a hashable object gets us a random number, and that number is the same every time. We can take an item we want to store in our dictionary, hash the key for that item, and then put the item into the index of the underlying list based on what the hash is. And we can easily get this item in constant time, meaning no matter how many items we're storing in our dictionary, we can retrieve the item that we are trying to get in the same amount of time, but hashing the key and getting the item in the corresponding index. This runs into a problem, though, if the data type of our key isn't hashable. If the key isn't hashable, then we can't figure out which index in our underlying data structure to use to store the value. So why isn't a list hashable? As I mentioned before, it's because it's mutable, essentially. Or rather, most correctly, it's because it doesn't implement the hash function. But I think the reason it doesn't implement the hash function is because it's mutable. It can change. We can add elements to it or delete elements from it or change the elements that are stored in the indices of our list. If we change the members of the list, then the hash, if the list were hashable, would be different. And a different and inconsistent hash would be worse than useless because it would be misleading. Conversely, a tuple is immutable. It cannot change, and therefore a tuple is also hashable in Python. And since a tuple is hashable, it can be used as a key in a dictionary. So this is kind of a long way of saying that one advantage of tuples over lists is that they can be used as keys in a dictionary. If you want to use a sequence as a key in your dictionary, you must use a tuple instead of a list. So for example, suppose that we wanted a data structure where we stored stock prices. The key might be a stock symbol and a date, and the value would be the stock price information for that day, as in the below example. We couldn't use a list to contain our sequence, but we could use a tuple. Thus, if we wanted to iterate over a range of dates, we could combine each date with all of the stock symbols that we were interested in and represent that sequence, that pair of date and stock symbol, as a tuple. And then we could retrieve a collection of stock price objects that we wanted to see. And so here's that example where we have this dictionary called the stock prices. And here we have a key, which is a stock symbol and a date. And that key is storing a value of this stock price information, the high, the low, the market cap. So let's just execute this. We can see that wouldn't work. That would give us a type error if we tried to do this using a list. It's an unhashable type list. But once we go back to using our tuple, this will just succeed. So the next point is that tuples and lists are similarly fast. It's a common myth to hear, and you might see it if you search Google for the question, why use tuples instead of lists? You might see that tuples are faster than lists. But actually, in my experiment, that doesn't really seem to be true. Lists and tuples are similarly fast. So there are a few ways that a sequence could be considered to be fast. How long it takes to create, iterating over the sequence, unpacking the sequence, slicing the sequence, sorting the sequence, checking membership in the sequence. But in all these cases, I found that lists and tuples are roughly similar. So there are some details below. And here, what I'm doing is just defining a few functions that I'll use to check how quick lists versus tuples are. So here I have this sum sequence function where I'm just iterating over all the members in a sequence. And here's the functional version of that same thing where I'm using the reduce function to sum up all the members of a sequence. Excuse me, this is the unpack test where I'm using the unpack notation, where I have 3 variables here. And if I supply a sequence with 3 members, it'll automatically be unpacked into these 3 variables, meaning A would get the first value of the sequence, B the second, and C the third. Excuse me. In this function, the mirror sequence, I'm appending to the original sequence the reverse of the sequence. So this is just a few operations, appending and slicing and reversing. And then this function I'm just using sometimes to help me estimate the time of a particular function. It takes a function as an input. It takes a number of iterations that I want to try testing the function for, and it takes a tuple, by default an empty tuple, for arguments that will be supplied to the function. So what this function does, it's going to record the time when you start, and then for the number of, for one time for each integer in the range between 0 and I, the number of iterations you want to execute, we're going to invoke f, the function you passed, with, and this asterisk here is the unpack operator of the arguments you supplied. So if we supplied 2 arguments here, these 2 would be unpacked and supplied to our function f. So that's a way to let us say, and then what we'll do is we'll return the time at the end when we're returning our function, reduced by the start time, and then divided by the number I, which will give us the time per iteration. So we'll execute this maybe 100 times, and we'll sum up the total time that it took, the difference between the end and the start, and divide it by 100, so we figure out the time per execution of this loop. And then we're just multiplying by this number to convert to microseconds. So we'll be able to say how many microseconds did this function take on average. And Python and the Jupyter notebook that I'm using actually have some functions that work kind of similar to this. But I'll show you why I'm using this function a bit later. Anyway, so let's look at creating lists. Again, I'm using a generator expression here to create a list of the estimated time to create a random sequence of length, 10,000 times, creating a random sequence of different sizes for n between 1 and 100 incrementing by 10. So we're creating a list. We are 10,000 times creating a list of size 1, of size 11, of size 21, and so on. And then we're doing the same thing for tuples to get tuple creation time. Then again, using matplotlib, we're creating the x-axis of the same range we had here. And we're just going to put next to each other the time in microseconds that it took to create one of these lists. And so we see that actually if you have only one element, well then maybe it is substantially faster to use, in this case, a list rather than it's substantially faster to use a tuple in orange rather than a list if you have a single element. But for every other case, lists and tuples are pretty similar, and it can vary back and forth. Sometimes a list is a bit faster. Sometimes they're almost the same. Sometimes a tuple is a bit faster. So creating one element sequences, sure, use a tuple. But even then, this is only saving you 8 microseconds. So it's not that valuable even then, unless you're creating billions and billions of single element sequences for some reason. Yeah, that's just kind of a graphical representation of the creation times. And I'm not going to bother to make a graph of all the different times, because as you'll see, they're all pretty similar. So here I'm creating the 3-item tuple and the 3-item list with the same 3 items. And I'm going to use that to use the estimate time function with the unpack test that we saw before. So this function, again, is just going to unpack my 3-item tuple or my 3-item list. And we'll see that they take approximately the same amount of time. Here, again, these are in microseconds, so I guess this is 0.1 microseconds on average to unpack a tuple, and it's 0.1 microseconds to unpack a list too. So unpacking is pretty similar. Here I'm just creating a random list and a random tuple that we'll use later on. And here I'm using the built-in function, which may be a bit nicer to use than estimate time if we don't have to give it different arguments programmatically. Here we're using the built-in time function to use the sum sequence. And remember, this is basically just iterating over all the items in our list. And we see it's 2.84 microseconds to iterate over all of the items in a random list. And we're at 7 microseconds to iterate over all the items in using the functional version of our list, of our sum sequence. So the imperative, I think you would call it, the non-functional version, is substantially faster, but our times for a list are 2.8 microseconds or 7 microseconds. And when we compare that to our random tuple, we're 2.9 to just iterate over, almost 3 microseconds to just iterate over our random tuple. And we're about 7.2 microseconds to do the functional version of the same thing. So same pattern, that the functional is multiple times slower, but 2.9 versus 2.8 microseconds, and we're within the standard deviation. So there's not really significant or meaningful difference between the time it takes to iterate over a random list versus a tuple. Here we're looking at the unpack test again, and this is just using the timeit function instead of my estimate time. And sure enough, we see similar results: 108 nanoseconds for the tuple, 102 nanoseconds for the 3-item list, and again, we're within the standard deviation. The mirror sequence function, it's a pretty similar story. With the list, we're at 757 nanoseconds compared to 794 for the tuple. Here we're just using the min and max functions, basically to search our sequence and to find the smallest and the largest elements. And again, we see 2.94 for the tuple, 2.84 for the list. List is slightly faster, I guess, but it's within the standard deviation. So the variance is meaningless, just noise really. They're almost exactly the same. And here we're sorting the list and the tuple, and we see they're within a millisecond of each other, again within the standard deviation. So here, this example is one I found by just Googling why use a tuple instead of a list. And I saw a Stack Overflow answer that said, well, a tuple is faster. And what they gave as an example for a tuple being faster is this statement. They said you can check it yourself and see that a tuple is faster. And so what the timeit function does is it's just going to execute this function this number of times and then tell us how long it took. So you can see there is actually something of it's a more significant difference than some of these other values we saw. In this case, it actually seems like the list is slightly faster. I don't know why that is. but it's not a consistent difference. So here I think there's just something going on where consistently using the same range is giving you different times. Because if we follow the same pattern with a string instead of a range, we see that the numbers are almost exactly the same. 0.26 versus 0.22. This time the list is again slightly faster. But either way, these are not huge differences. Remember, we have to run it however many times this is. Let's see, 1,000,000 times to get a 1/10 of a millisecond difference. Or in this case, we run it 1,000,000 times to get 4/100ths of a millisecond difference. It's just not a very significant difference in terms of time. So in other words, some scenarios, maybe it's a bit faster to create lists than tuples, but it's never more than, 1/10 of a millisecond or something. It's never more than like a fraction of time. Pretty much its lists and tuples are effectively the same to use in terms of time, as far as I can tell. So this has been a quick look at tuples in Python and how they compare to Python's lists. If you enjoyed this video or learned something from it, let me know by clicking the like button. If you want to see more content in a similar style, go ahead and subscribe. Thanks for your time.